A passenger train weighing 800 tons hurtles toward a station platform at 160 kilometers per hour. The braking marker appears ahead, a distance that, given the train's mass and velocity, seems impossibly short. Yet within seconds, the train glides to a smooth, controlled stop. That naturally raises a question. How does a train actually brake? And this is where the most common misconception needs to be cleared up right away. A train does not stop the way a car does. Wheel brakes are only one part of a complex, multi-layered system. If a train relied on friction brakes alone, safe stopping would simply not be possible. Train braking is a sequential process that begins long before the wheels ever make contact with the brake discs. It involves driver calculations, electrical systems, mechanics, hydraulics, electronics, and even track conditions, all working together. Each element comes into play at a very specific moment, and an error at any stage can increase the stopping distance by hundreds of meters. Preparation for stopping starts well before the driver reaches for the brake handle. Pilots calculate braking points based on route knowledge, train weight, gradient profiles, and current weather conditions. This is critical because even a small miscalculation in deceleration timing can force reliance on emergency systems later on. Modern trains display gradient information and speed restrictions in the cab, but experienced drivers memorize route profiles. They know precisely where downhill sections demand earlier braking and where level track permits shorter stopping distances. That is why route familiarization is not optional. It is a fundamental safety requirement. The first tool used to slow the train is not friction, but electricity. If you're interested in understanding how complex machines actually work beyond simplified myths, this is exactly what we focus on. On electric and diesel-electric trains, the traction motors that normally propel the train can reverse their function. Instead of consuming electricity to generate motion, they act as generators, converting the train's kinetic energy back into electrical current. This is regenerative braking. The recovered energy either feeds back into the overhead catenary or dissipates through resistor banks mounted on the roof or under frame. In effect, the train begins shedding speed without any mechanical contact, long before friction brakes engage. As a result, it enters the mechanical braking phase at lower velocity, which is crucial for everything that follows. Regenerative braking is not simply an efficiency feature. Modern electric trains use regenerative systems as the primary deceleration method during normal service braking. The system can handle a significant portion of the total braking effort, sometimes contributing up to 60 or 70% of deceleration at higher speeds. But there is a trade-off. Regenerative braking effectiveness drops as speed decreases. At very low speeds, the system produces insufficient retarding force. That is why mechanical brakes must always be available to complete the stop. And this choice is far from accidental. The moment regenerative capacity is exhausted marks the transition to the second phase of deceleration. At that instant, friction brakes must take over the remaining workload, entering an extreme operating regime and experiencing enormous loads. Train disc brakes are not simple pads like on a car, but massive multi-disc assemblies designed to absorb immense amounts of energy. On freight locomotives and passenger coaches, these brakes consist of steel or cast iron discs clamped by hydraulically or pneumatically actuated brake pads. High-speed trains often use composite materials designed to withstand extreme thermal loads. During heavy braking, we're talking about hundreds of megajoules of kinetic energy being converted into heat in just seconds. In other words, a huge portion of the train's momentum is dissipated as thermal energy in a very short time. After hard braking, disk temperatures can reach 300 to 600 degrees Celsius. That is why after aggressive braking events, trains may sometimes need to pause before departure to allow cooling. Operating with overheated brakes reduces friction effectiveness, a phenomenon known as brake fade. Excessive heat can also cause metallurgical changes in disc materials and increases the risk of thermal cracking. For that reason, brake temperature is monitored either manually by infrared inspection or automatically via onboard sensors, and decisions about continued operation are made strictly by procedure. And here's the problem. No human driver can precisely modulate braking force across multiple axles under dynamic conditions. Track adhesion varies with rail wetness, temperature, and contamination. Load distribution shifts during braking. That is why trains use automatic braking control systems. The driver selects a braking rate, and the system computes the required brake cylinder pressure based on speed, estimated train mass, and gradient. The goal is not maximum deceleration at any cost, but predictable, controlled stopping with stable wheel behavior and a safe margin in distance. On top of that, there is a wheel slide protection system, similar in principle to automotive anti-lock braking, but far more sensitive. It monitors the rotational speed of each individual wheel and compares it to the train's actual ground speed. If a wheel decelerates faster than the train body, the system detects an impending skid and instantly reduces brake pressure to that axle. Even a brief wheel lock at high speed can lead to loss of directional control or severe wheel damage in the form of flat spots. And here is the counterintuitive fact. A locked wheel does not stop the train faster. Rolling friction between steel wheel and steel rail is higher than sliding friction. A skidding wheel creates a contact patch that heats, oxidizes, and becomes less effective. The wheel slide protection system prevents this by maintaining each wheel at the edge of maximum braking without crossing into the slide regime. This happens dozens of times per second during heavy braking. The system is that precise. When adhesion between wheel and rail drops due to environmental conditions, mechanical intervention becomes necessary. That is where sanding systems come into play. Modern trains carry pressurized reservoirs of fine sand that can be dispensed precisely between the wheel and rail contact patch. The sand particles increase the friction coefficient temporarily, allowing higher braking forces without wheel slip. This becomes especially critical during autumn, when organic material from fallen leaves creates a slippery layer on the rail surface comparable to ice. Railway operators refer to this period as leaf fall season, and track maintenance crews treat rails with high-pressure water jets and apply specialized friction-enhancing compounds, because without these measures, braking distances can double. Sand application is metered carefully. Too much sand can clog the track circuit electrical systems used for signaling. Too little provides insufficient friction enhancement. The dispensing rate is typically controlled automatically based on wheel slip detection, though drivers can also activate sanding manually in anticipation of known low-adhesion sections. That layered control is exactly what makes the system so reliable. Beyond service braking, trains carry a separate emergency braking system. This is not simply a stronger version of the service brake. Emergency braking activates every available brake on every vehicle simultaneously and irreversibly. Once initiated, the emergency brake cannot be released until the train comes to a complete stop and the system is manually reset. Brake pipe pressure drops to zero across the entire train length, forcing all brake cylinders to maximum application through fail-safe spring mechanisms. Emergency braking is reserved for genuine emergencies because the deceleration forces can injure standing passengers and cause cargo shifting in freight consists. The emergency system also includes vigilance controls. If the driver becomes incapacitated and fails to acknowledge periodic alertness prompts, the system automatically triggers emergency braking. On modern trains, this vigilance function operates continuously, requiring the driver to interact with controls at regular intervals, Failure to respond results in an audible alarm followed by automatic brake application within seconds. It is a last resort solution, but it has already saved dozens of crews and passengers. The track itself is also an active part of the braking system. It is not just steel rails on wooden sleepers, but an engineered surface with specific gradient profiles, cant angles, and friction characteristics. Braking distances are calculated for each route section and programmed into the signaling system. Signals are positioned at precisely calculated distances that account for the maximum permitted speed, typical train mass, and gradient at that location. If a driver fails to begin braking at the appropriate distance marker, automatic train protection systems can intervene and apply the brakes without driver input, because human error must always have a technical safeguard. Track gradient has enormous influence on braking performance. A 1% downhill grade requires significantly earlier braking initiation than level track. Drivers must know their route gradients, either from memory or cab display systems. On mountain routes, braking distances can increase by 50% or more compared to flat terrain. That is why gradient mastery is not optional knowledge. It is survival skill. Wet rail conditions reduce adhesion by 20 to 40%. Rain creates a thin water film that acts as a lubricant between wheel and rail. Heavy rainfall can reduce friction to the point where wheel slide protection systems activate continuously, even under moderate braking. That is why speed restrictions are often imposed during severe weather. Some railways incorporate emergency runaway sidings or sand traps on steep grades. These are designed as last resort fail-safes. A sand trap consists of a deep bed of loose sand positioned at the end of a siding. A runaway train diverted into the trap sinks into the sand, dissipating kinetic energy rapidly without catastrophic structural damage. The key point is this: train braking is not one mechanism. It is a system. Every element supports the others. If one becomes less effective due to conditions, the rest compensate. That layered redundancy is exactly what makes railway operations so safe. So a train does not stop because it has powerful brakes. It stops because of a carefully calculated scenario in which regenerative systems, disc brakes, wheel slide protection, sanding, track gradients, and signaling all work together. It is not a single hard application of friction. It is controlled dissipation of massive kinetic energy, step by step, with no room for mistakes. And if you enjoyed the video, don't forget to subscribe to the channel and leave a like.